If you've dragged yourself out of bed on a Friday morning to come to this session, I don't have to tell you the truth behind this particular slide. All of us in this room know that the security landscape is completely different from what it was just 15 to 20 years ago. We've moved from a world where our biggest threats were coming from kiddie hackers trying to make a name for themselves somewhere in the Midwest, and organized crime trying to steal money and assets, to one where the primary threats are coming from state-sponsored terrorism, state-sponsored cyber espionage, and cyber attacks. In the past, the types of businesses that were targeted were the really big ones, the ones that would hit the front page of the Wall Street Journal or the New York Times. Today, every organization of any size is being targeted by folks who want to do you harm. And yet, organizations who have massive budgets to spend on security are struggling to contain this problem. Everyone, of course, knows that Sony was hacked, doing great damage to their infrastructure and to their intellectual property. The White House was hacked. Anthem, Blue Shield, Blue Cross, any number of insurance companies have been hacked. Lockheed Martin, a major defense contractor, hacked. Aramco, the largest Saudi oil company, hacked. An air-gapped network, the Bushehr nuclear reactor in Iran, was hacked. The NSA, whose very existence is to contain security threats, hacked. Facebook, Apple, Google, and Microsoft, every one of us has been hacked. Windows 10 is making a substantial number of investments to try to address these core problems. We have three pillars of investments that you've probably heard about in other sessions if you've been to any of the other talks from my peers from the Windows security team. First, working with our industry partners, including Google, as part of the FIDO Alliance, Microsoft is trying to advance the security of identities, moving away from a world where we are reliant on passwords for authentication, both to our systems as well as to all of our services and remote sites that we need to access as users, both in the consumer space and as business users. Information protection. We are making investments to try to allow you as an organization to have greater control over who has access to your important data and what they can do with that data on their systems. Setting policy that allows you to specify what applications specifically are considered corporate applications, trusted to access secured content. And we will block things such as copy and paste from occurring between one application that is trusted, that can show your sensitive data, and another application that is untrusted or unknown to you as an organization. And last but not least, and the topic of this session, threat resistance. DeviceGuard is very specifically intended to help us as an industry and help you as our customers better secure your enterprise assets against the threat of malware and attacks.
Okay, so super simple demo. I've taken my laptop with me on a trip. I want to watch a movie, let's say. So I plug in this USB stick that I've gotten, and I'll just load up VLC. Now, I have nothing against VLC. And of course, I don't know who published this. I don't really care. I just want to watch my movie, and boom, VLC is installing. This was a super common threat vector a few years ago, especially, I would say. People, to watch their movie, they need they need to have, this codec, and this codec happens to be an executable, and you're just going to click through whatever things you need in order to watch that show. So, in the name of simple demo, what happens with a device guard system? Any guesses? Exactly. Depends what device guard wants to happen. Okay, so
Scott, in the background, has switched over to a second computer, which we've actually already set up with device guard policy, enforcing our corporate enterprise image.
Right. And it's as simple as you're not allowed to run this application. Now, there's a lot of stuff going behind the scenes there, which we'll get into in more depth, and we'll show you how you set this up. But we're just trying to show that we're really changing the way people think about how much they own their machine. This is an admin user. They have full privileges on the box. They still can't run this application. Yes, the message is being changed. You're not the only one to notice the bad text. But, sorry,
but if your question is it customizable, not in this release. Right. But we have certainly heard the feedback from a number of you. So what is device guard specifically? Device guard is not actually just a single feature. It is not something that you just push a button and turn it on. It's a combination of things that, of both hardware security features and software security features that when they're configured together are able to lock down your systems to have the most secure and resistant system possible. What we wanted to do was learn from our mobile device peers, which come locked down today, whether you're talking about an iOS device or a Windows Phone device or Windows RT, from our somewhat failed experience in Windows 8. We want to bring the mobile-like security features to x86 and x64 systems, but allowing you as enterprise organizations to configure the policy that determines what is trusted to run, so that the systems essentially are locked down to only running applications you trust. The example Scott showed, we could have just as easily shown one like you would have seen in Monday's keynote, where it was actually malware they were trying to protect against. In that particular case, Scott was just showing that the diversity of applications that users are installing on your systems can themselves represent a threat, because you don't know how they're patched. You don't know what applications necessarily have vulnerabilities that can be exploited by malware. So by controlling this policy and allowing you to lock down a system tightly, you're able to protect against those malware threats and those vulnerabilities. So there are a number of different parts that build up the device guard solution. As I said, we start with a base set of hardware security. Much of this was actually things that we introduced along with our industry partners in the Windows 8 timeframe, and even before that, starting from TPM, hardware security module for doing cryptographic operations. In Windows 8, we moved from the legacy BIOS that had been around for decades to UEFI, a more modern BIOS, which, along with other features, allowed us to actually take advantage of a feature that Scott will talk about in a moment called UEFI Secure Boot. After the hardware security features, we have now exposed controls over what we call code integrity. Again, Scott will talk about that a bit more. And then virtualization-based security, which is a completely new hardware-enforced security boundary that actually allows us to protect critical parts of the operating system, including code integrity. And all of this has been exposed for manageability through the tools and management tools and services that you expect: MDM, group policy, and PowerShell.
Okay, so Jeffrey mentioned code integrity. If you look at this slide, this is basically everything that runs on your computer. From the earliest bit of boot, the firmware before Windows is even involved, up through booting the system into Windows, up into the kernel mode components, the user mode components, etc. If you go back to, say, XP, none of this was validated. Everything that ran was just taking the binary and executing it. When you move up to, say, Windows 7, we introduced kernel mode code integrity. So anything that wanted to run in the kernel mode on a 64-bit system had to be from a trusted publisher and signed. And we introduced AppLocker. You see AppLocker to the far right, which gave you some control over which applications you could run on that particular system, mostly just for standard users, and it didn't give you control over anything sort of higher level, like any system processes, et cetera, you couldn't control with AppLocker at the time. Windows 8, we added platform secure boot, which is really the very earliest part of the boot process, and UEFI secure boot. So that's only loading up a trusted OS loader. So that eliminated things like MBR rootkits, et cetera. And what we're really adding here in Windows 10 is that middle piece and the control over all of it. So the UMCI stands for User Mode Code Integrity. Like Jeffrey said, that's already the technology we have on, for example, our mobile platform, making sure that everything that runs in user mode is validated before it's allowed to run. And you can see the red box. We're also giving you just more control over what those applications are. So traditionally, kernel mode code integrity, anything that was trusted by one of our third-party partners, anything that was signed by the Microsoft Hardware Qualification Lab. So basically, any driver that anybody had ever written for any Windows device would work on your device. So somebody could take a driver that really had no reason to be on your device, but they knew was vulnerable, gave access to secrets on your system, bring it over to your device, and it would run. With Windows 10, we're giving you control over the kernel components as well as the user components. One of the questions that comes up is, what about scripts? Scripts can sometimes be just as dangerous as binary code. You can even launch executable code from scripts. So in Windows 10, the script hosts have been enlightened. So the Windows script host, which is what hosts VB script, JavaScript, Windows script files, will only run signed scripts that are signed by a trusted publisher, a certificate that you trust as an organization. Similar for MSIs, so even just installing software, you can run scripts that can do dangerous things. We want to block those if you don't approve them. PowerShell, we know that's a powerful tool for a lot of you, and you probably don't want to completely lose PowerShell. So it will be in what's called constrained language mode. That basically allows you to do all the normal things you can do with PowerShell in the core language set, but it cuts off a lot of the extensions. So you won't be able to launch .NET stuff, call into Win32 APIs, unless it's a signed PowerShell script. So you can still do all that stuff if you sign your PowerShell script with a trusted signer, but even without doing that, you can still do have a lot of the power of PowerShell to control your systems and configure them. .bat and .cmd scripts are not restricted. That's because you can't really launch code from them. You can do certain things that you might not want done with them, and if you want that extra layer of control, that's where AppLocker can come in and lock down individual scripts rather than just having the blanket policies. One other thing to note is this is for all the built-in Windows script hosts. If you install any other script hosts from third parties, all we can really control is that script host is allowed to run or not. That's what we can block or not. So if you choose to let a particular script host run, it can run other stuff, and so you need to take that into consideration when you're making that security decision.
So we called this session Dropping the Hammer on malware, and the choice of the word hammer is actually applicable because this really does represent a specific, very powerful tool to lock down systems, and it's not going to be one that you're going to find broadly applicable necessarily, depending on the use cases that you allow your users to employ. So where would I find DeviceGuard to be useful and applicable in my organization? So certainly on fixed workload systems, so things like cash registers, for example, ATM machines, those types of things that you know should have a finite set of software installed on them should not be changing all that frequently. They're not getting updated. The applications are not changing. There's either no user interaction whatsoever on the system, no user account, or certainly no administrative user. And again, there's low churn in the type of code that's running. Device Guard fully applies here. You can run the entire stack of Device Guard, all of the features that make up what we call Device Guard, from the virtualization-based security, enforcing protection of the kernel mode code integrity, all the way up to your enforced kernel mode and user mode code integrity policy. Similarly, if you manage your user workstations in a very tight manner, so your users can perhaps install applications, but the applications all are coming from a managed catalog, managed through a configuration manager or a Windows Intune or any of their competitors. And you can predict and you know what software is supposed to be present. You have a good handle on what hardware diversity exists in the system. Again, it'll be very applicable to take Device Guard and build it out for those environments. As we broaden out beyond those scenarios, it becomes a little less useful to employ Device Guard in its full entirety. So if you give your users great flexibility and control over their systems, you are releasing some of the control that Device Guard is intended to offer. If you're allowing the users to bring their own hardware and install third-party kernel mode drivers in order to use that hardware, you've given up control over the kernel mode. If you allow them to install any random application, you're giving over control of the user mode code integrity space. So again, here, while you might be able to take advantage of some of the features of Device Guard, you won't be able to employ a fully locked down environment and really, as I said, bring that hammer down. What you can do is you can take some of the features and, for example, run in an audit mode. So Scott will show in a moment that on a Device Guard protected system, you can actually run it in either audit or enforcement mode. And in either case, there's event logs generated that identify any binaries that violated the policy. And so you can get some very rich data about what the drivers and applications that users are installing are actually attempting to do. You might have some more flexibility around using our virtualization-based security. We'll talk more about that towards the end of this session. So you'll kind of understand where that might be applicable. But again, that the user mode code integrity and the kernel mode code integrity policy is unlikely that you'll be able to enforce with a very tight policy. And finally, BYOD. In this particular case, Device Guard just is not applicable. In many cases, the hardware won't even be able to run some parts of what makes up Device Guard, specifically the virtualization-based security. But in either case, you as an organization don't have the contractual agreement with the user to take full control of their personal device. So thinking about how and where to leverage Device Guard's features is the most important thing for you to get right as an organization. Know specifically what targets you want to tackle with a locked down environment. You can use PowerShell scripts to actually generate the policies from systems that have been built out to reflect what an ideal system looks like across the diversity of hardware that you have in your environment. So if you have if users are able to obtain one of maybe 5 types of laptops, for example, you could generate policies to capture what those images look like across each of those hardware categories, and then either merge the policies together to create one Uber policy that's applicable across all your machines, trading off some of the security lockdown mechanisms in case, as Scott said, there were vulnerabilities in, for example, a kernel mode driver that's applicable on one type of laptop and not on others. Or you could actually take those individual policies and target them to that class of system. So there's a great deal of flexibility in what you can do, and you have to make the decisions for your organization for how to balance manageability and lockdown security. Once you've generated that initial policy, ideally you want to run it in audit mode, at least on a set of systems. And the reason for this is oftentimes the initial policy, the initial scan, may not catch everything that is eventually going to be installed onto that system. There are certain applications, for example, that will download other executables and other binaries, which may be signed differently from the applications or the installer that was present on the system. So you want to be able to learn over time and enrich your policy to now extend it to support those additional things. Again, you can use our PowerShell scripts to create policies from your audit event logs and then merge those into the original policy and extend it to cover everything that you expect to run on your devices. And then finally, once you know that your policy appears to be operating as you expect, the audit events would have blocked the things that you wanted to block and yet allowed the things that you expect your users to be able to do. Then you can put your policy into an enforcement mode. At the core of our PowerShell scripts that I keep talking about, at least for generation of the policies, there's really three that you're going to interact with primarily. New CI policy, which can be run both to do a full scan of a system, as well as to create a policy from audit events. And then merge CI policy to take one or more policies that have been generated, merge them together to create an Uber policy that you apply. And then the last one is set rule option. So you use that to manipulate some of the additional controls that we expose through device guard.
Okay, I'm going to walk you through some of this. We get right down into the nitty-gritty PowerShell. Okay, so here's the system. We've actually already deployed an audit policy, but I'll show you the initial setup, steps, etc. Run PowerShell. So here's the commands I'm going to run. We've typed them out. A, so you can see them more easily. B, so that I won't make any typos. First, we're creating a shadow copy of the volume. You can also scan, for example, an offline volume to remove any sort of access violations, etc. So that's step one. We're just creating a shadow copy of the volume so we can access any in-use files. Second step is the scan. So the options we're seeing here, I'll just do a zoom in, are new CI policy. So new CI policy, as Jeffrey said, you can use it to create a policy from a full scan of a system or just looking at individual files or from the audit log. The level we're choosing is PCA certificate, so we're doing it at the certificate level. You can do it down to the file level or even the hash level. The obvious problem with doing something at, say, the hash level is that if any file gets updated, it'll no longer be trusted on your system. So in order to, say, be able to easily update the system without having to update the policy every time you want to change a binary, the easiest thing is to have the certificate level, and then you can just sign your new binaries and they'll run in all your systems. The file path is just where the file is going to go. Scan path is scanning the shadow copy rather than the regular disk, but you can aim it to any directory. And then the -user PEs, that's basically looking for both the kernel mode binaries and the user mode binaries when you add the user PEs option. So I'll do this. You see some yellow text. If you do this sort of today, you'll see a fair amount of yellow text where we're still... Oh, yeah. So, for example, it's not being able to open the Hyper file. We're fixing most of that, but the fact is sometimes we do come across directories that for one reason or another we can't scan, and that's part of where the audit mode comes in. So I'll leave that scanning in the background. We've pre-scanned it, so you don't have to wait for 20 minutes. It's scanning every single file on the system, looking to see if it's a PECOF, so that's the portable executable. So basically, any binary file on the system, it's looking at checking whether that binary file is a user mode binary or kernel mode binary, and creating the appropriate rules in the policy. So here's a pre-generated policy. It is, let's see. It's an XML. So Jeffrey at the beginning mentioned there's a few things that we call rule options. There's basically two main parts of the policy. One is the sort of rules that you're setting. You see here we have unsigned system integrity policy. We'll talk more about whether you want to sign your policy or not sign your policy. Basically, signing your policy gives you the extra level of protection against even the administrator on this box, and potentially even against a physical attacker. So even an administrator with a physical box, they want to boot into some other media and try to get past your system because they really want to run that program. You could even block that with signed policies. Enable audit mode. By default, we turn on audit mode because, like I mentioned, this is a powerful tool. You can lock out administrators. That means you can lock yourself out. And you don't want that to happen. So we start you off in audit mode, and then when you're ready to enforce, you can do that later. Enable advanced boot menus options. Basically, one of the ways to bypass code integrity in general is the old F8 menu, and then you can say disable, signature verifications. And that's a good thing to get yourself out of trouble, but it's also a way to bypass the system, so we can disable even those menus in the pre-OS environment. All right, and then the policy itself basically consists of a number of certificate authorities that were found to have scanned the files on your system. So we've got like the Microsoft Development PCA. This is still a development build, so we've got that is the one that signed it. We've got the VeriSign Class 3. That's a common signer of drivers. The Windows Hardware Compatibility Lab. That's the Microsoft WCA lab. So basically, you trust all these certificate authorities, and then later down in the file, it'll say whether it's trusted for user mode or kernel mode or both. Okay, so we've got this policy. We've already applied the policy on this system.
And again, this policy is right now in audit mode.
Right. So we've got the policy running in audit mode, which I don't know if I pointed out on the original when I was showing you the. You see, one of the options is audit mode. Yeah, so I did point that out before. So we've got the policy running in audit mode. So now what you can do is look in the event log. Now we don't expect you to go looking in the event log all the time and parsing these events, but basically you see in the event log there's some programs that were attempted to run and were blocked, or would have been blocked. It says, however, due to system integrity auditing policy, the image is allowed to load. So this tells you everything that code integrity would have blocked if you were in enforcement mode. And you can go look at that and decide if those are things you wanted to block or those are things you actually wanted to allow to run. If the things you actually wanted to allow to run, then what you can do is update your policy based on what you found in the audit event. So you look at the audit log and you say, oh, they were trying to run these applications that really we do want to allow to run. We need to be able to run Adobe Reader or whatever. So you can, rather than, say, trying to install Adobe Reader, there's a couple ways you can expand your policy. But a simple way is to just base it on the audit log. So here's the second script, demo 2. So in this case, I'm calling new CI policy again, but I'm basing it on the audit log. So you see new CI policy minus audit. So that means pull it from the audit log. And in this case, we've actually chosen to do the level hash. We don't know exactly why those files didn't show up. Perhaps they weren't signed by a recognized signer. So instead of doing it for the CA in this particular example, we're just doing it by the hash. Like I said, the problem with that in general is if you update those files, you'll need to make sure you update your policy at the same time. Otherwise, it'll be blocked. And we're going to send it to auditpolicy.xml, and we're including the user P. Actually, we're not going to. OK. Yes.
Someone sends an infected PDF because you're running an older version of Adobe Reader.
Right, so the question is, say you're allowing Adobe Reader, someone sends an infected PDF. So, so there's two things there. One is, and we're not showing it here, but you actually can specify versions also. So you can get down to the version and file level and say, I only want to run, Adobe Reader version 10 and above. So that's the mitigation against the older version of Adobe. In terms of if you do have a vulnerable component, it's still possible for that component to, obviously do things to your system acting as Adobe, right? We'll talk a little bit later about what virtualization-based security does in terms of preventing any of those vulnerabilities from getting into the kernel mode space. Basically, we have some additional protections so that kernel mode, if you've got virtualization-based security enabled, even if there's vulnerable components, you won't be able to get in and add your code directly into kernel mode. And we'll cover that in a bit. But in user mode, it is true. If you have a vulnerable component, if you've allowed something that's vulnerable, and somebody takes advantage of that vulnerability, there's still a possibility for them to, run something that you don't want them to run.
Is there a UI that we can actually control this through, or will there be one?
So the next question's on the UI. A fairly obvious question because we're showing you all this PowerShell stuff. So there isn't a UI within Windows 10. We are going to be documenting the format, so it's possible for other management tools to provide some of that. And we are also taking some feedback on sort of what UI elements would be the most useful for you. Obviously, we don't expect end users to ever see any of this. So to some degree, it's you guys who would have to feel the pain. But yeah, today there's no UI.
And to be perfectly honest, that was actually somewhat by design. Because of how locked down this will make your systems, it's such a powerful tool, and it can cause such significant problems if you get it wrong, that we really want you to be thoughtful about how you're approaching the problem of engaging with device guard. And we really want to work with management tools to try to, over time, generate really rich ways of creating and managing these policies.
Right.
Sorry, one other question over here, yeah?
Speaking of management tools, what I would see is the direct client like System Center, where guess what? I have an app that I've spent the time to package. Is there any thought on the roadmap to make it such that when I deploy Adobe, it automatically creates the caches for me?
Yeah.
It auto merges the new policy so that when I install Adobe on machine 1, it has Adobe allowed, but on the 10,000 other machines that we didn't install Adobe, it's not allowed.
Yeah. So the question is, given an application like a configuration manager or some other management product where you have your catalog of what's allowed, the applications that are supposed to be on the systems, getting that to actually be the way that the policy is generated and updated, that's certainly the scenario that we're talking to the configuration manager team about. They're on a completely different ship schedule from Windows, of course, and so I don't know what their timeline would be to actually implement that, but that's kind of the killer scenario that we want to light up over time. It's not there yet.
I've talked with them, and they say that they're being restricted because the OS team won't allow them to do that, so it sounds like there's nothing.
So we're talking to the right people over there. You may have been talking to someone who's not plugged in, but that's not true. So we absolutely will work with the config manager team. And it's just PowerShell. So there's nothing that restricts configuration manager or any other management tool from generating these policies. And as Scott said, we'll be documenting for software vendors who build these management tools the schema for generating the policies. So there shouldn't be any limitations to getting that wired up.
OK, so the next thing I'm going to show you is just we've created that audit policy based on the audit log. And now we're going to merge the policies. So you see merge CI policy and then the paths to the two existing policies and the path to the policy that you get output. So pretty simple command. In this example, we're showing it for the original policy from the scan plus the policy that you got from the audit log. But you can also take policies from 2 different machines or 10 different machines. merge them all together. We'll eliminate the redundancies, et cetera, obviously, and then have sort of a master policy. So if you have, let's say, 5 standard machines, maybe in your server operations center or something, you could scan all those machines and send them all the same policy to simplify rather than having to target the right policy to the right machine, for example. All right, so that just created the merged policy, and over here you can see, the merge policy we just created. It's got both the hash rules up at the top, as well as that we created from the audit log, as well as the signer rules that we'd created from the original scan. Okay, last couple of steps. To take this policy, which is an XML file, and actually use it on the system, we convert it to a binary format so that it's easier for the system to interpret during runtime, and we don't have any delays of recompiling and reinterpreting the XML. So there's a convert from command, which takes that policy and turns it into the binary, and you see it's super fast. The binary has been created already. And then you need to copy it into a particular location and file name, and it'll be picked up on reboot.
You missed the CP.
Yeah. All right. So now it's in the right location. When we reboot this system, that policy will apply. One of the questions we do get is, do we really need that reboot? And unfortunately, the answer is yes, for a couple of reasons. The biggest one really is about the security of the system. Like I was saying, we're trying to be in an environment where even things that happen during boot are locked down. Even the boot drivers that you're loading up, even the menu options that you have that allow you to normally bypass code integrity if you're the owner of a particular machine. So in order to have those enforcements happening that early, you really need to boot up the system. And let's see. So last thing, we already talked about it a little bit. There's the rule options. I think I showed you those rule options, but we can, if you're ready to go to enforcement, you've created this new policy that got your audit events, did your original scan. Your audit events now show clean. Everything's running just like you expect it to. You're ready to turn on enforcement. You go and set the rule option. You can actually literally just delete it out of the XML file also, but we've provided the command list just so you don't have any copy-paste errors when you're trying to mess with that with the text editor, let's say. So there's 10 rule options. I'll just show them to you. I'll zoom in a sec. So the minus help shows you the rule options. We have enabling UMCI, so that's turning on the user mode component in addition to the kernel mode code integrity, which is always enabled. Enable the boot mode, menu protections, and enable audit mode. Those are some of the key ones. So right now we have audit mode enabled. We want to turn off audit mode and start enforcing. So we're going to set rule option number 3, which you could see from this original list was audit mode. And we're deleting out of the file the rule option 3, which is audit mode. So you'll no longer be in audit mode. Now I need to convert this back into a binary file from the XML.
You can copy both commands at once, by the way.
And then copy it to that location and reboot the system, and we will be enforcing. But I'm not going to show you that yet because Jeffrey has more to talk about first.
So for convenience, the scripts that we just ran through, we've included in the deck, so you'll have those handy so you can play around with them. That's partially because the documentation is coming a little bit later. So the big problem that I think is going to limit adoption of this is the same problem that organizations who've tried to use AppLocker in the past face. As I earlier talked about, we're really trying to trying to target the malware space. Well, 96% of malware today, at least according to the malware that we have reported to us through the Defender team, is unsigned completely. So implementing a device guard policy automatically blocks 96% of malware, which is great, but it's the remaining 4% that's the really interesting stuff. Because those are ones that are signed by a legitimate signer. It may have been a case where a signing certificate was actually stolen from an organization, a legitimate independent software vendor. And so the policy that you have around your system actually allows you the granularity to block much higher than that 96%, up to and including the entirety of even signed malware. So unless one of your trusted, one of the certificates that you trust in your policy was compromised and used to sign a piece of code, malware on the system, your systems will be protected against running that malware. But just as most malware is unsigned today, I would be willing to wager that a lot of you in this room work for companies that also have, if not all of their line of business applications unsigned, probably a high number of them. Even within Microsoft, up to a few years ago, we had internal line of business applications that were not signed. But we moved and adopted that best practice. We are trying to move to a world with Device Guard where only signed code is going to run on a Windows system. And in order to do that, all of you have to adopt that best practice of signing. So there's a few additional challenges, right? Development in many of your organizations is decentralized. So you have pockets of developers who are building applications who may or may not be code signing. Additionally, I'm sure many of you have applications that have been around for a long time, that were packaged 10 years ago, unsigned. The developers may not even exist anymore. And you don't want to figure out how to repackage that application just to be able to sign it and distribute it for this. With respect to ISVs and other third parties, just because you want to trust an application from, or a set of applications from an Adobe, and I don't mean to keep picking on Adobe, but it's the only one that comes to my mind, you don't necessarily want to trust everything that Adobe has. So trusting the Adobe signer may not be the option that you want to go with. So what we're trying to do with Windows 10, I should say, what we are doing with Windows 10 is providing you tools that allow you to take applications that have been already packaged and run them through a process to create an additional signature that you can distribute with that application that's signed for your device guard systems. So you can take an application and not have to go through the burden of repackaging it. Doesn't matter if the developers still exist, and you can actually set it up so that it'll run on these systems. Yes?
Can that same process be used for app locker rules?
Can the same process, so the question is, can the same process be used for app locker rules? Actually, yes. The tool that we've provided for creating these signatures actually works for, can output app locker rules in addition to rules that work for device guard.
So what if the application's been already signed by a third party, but you want to sign it again with your own?
Yeah, so the question is, what if the application has already been signed by a third party, but you want to sign it with your own? So we'll cover that. Yes, last one.
Are you guys treating this as a standalone manifest, or are you doing an alternate data stream for embedding the data?
So the question is it kind of an alternate data stream, or is it embedded? So the tools that we provided allow you to generate the second option that's being displayed here, which is a catalog. So we believe this is the most efficient way of taking existing applications, including third parties, and appending your own signature and distributing that. There's two different types of signatures that you can work with. This is a primer for those of you who aren't familiar with it. So files can be embed signed. And those are the ones where if you right-click on the file in Windows Explorer and view properties, you'll see digital signatures. And that file actually has an embedded signature, which means the file itself, the binary, has been signed. In most cases, for many ISVs, you'll find that the binaries that are made up of their application, that are contained within their installer, have all individually been signed as well. So if you wanted to re-sign an Adobe, and I can't remember who asked the question, but if you wanted to re-sign an application that came from Adobe, the embedded option is probably not the ideal one, because you have to unpackage the entire installer, sign every one of those individual binaries, and then figure out how to repackage it and distribute it, right? But the installer itself has a lot of logic in there that you probably won't get right. So the catalog signature is a better option, because this allows you to generate essentially a manifest that is separate from the installer, separate from the binaries themselves, that identifies every file that was written as part of the installer process or the running of the application, and then sign that manifest and distribute it along with the application to your device guard systems and automatically allow for the applications to run. The last little bit before I go back into demo. So we're trying to, again, move to a world where we're simplifying the signing experience. So there's a couple of things here that are worth noting. So first of all, Microsoft, the Microsoft Store over time is going to be extended to also be able to ingest and distribute classic Windows apps. Those are the Win32 applications of today. So you could allow us to deal with the entire signing process on behalf of your organization once that's in place and it has been exposed for enterprise management. If you have your own internal enterprise signing PKI set up, you can, of course, use that today to get started with Device Guard. Ideally, incorporating it upstream in the development process. But again, if not, you can use our tools to generate catalogs and distribute them along with the line of business apps. And then last, Microsoft later this year will be standing up what we're calling the Device Guard Signing Portal. And this is a portal experience where you can go as an organization, register with Microsoft. We will actually generate a unique signing certificate for your organization, and we can handle the signing operations on your behalf. And all you submit are your catalog files that you've generated using our tooling. So you generate a catalog, you submit it to us, we return it signed, unique to your enterprise, so that you can distribute it with your applications. So let's take a look at how I take an existing application and make it work on a device guard system. Okay. So the tool that we've created is this one called Package Inspector. And it's fairly straightforward. One could argue it's almost dumb. We essentially allow you to start scanning your system, and we will monitor for any file write operation that occurs during the time that the scan is running. So, for example, I have 7-zip. 7-zip's a fairly popular zip tool that allows you to compress files into a catalog. Within your organization, you want to trust 7-zip, but you don't necessarily want to trust the signer of 7-zip. So what I can do is actually start scanning, and I'm going to install it to the C drive on this one. So I'm going to start Package Inspector scanning the C drive. And now, as I said, any binary write operation that occurs from this point until I stop the scan will actually be generated into this catalog file. So I'm from my removable drive, copy the installer over. All right. So installer is complete, but some applications, of course, do additional file write operations after being run. So just to be safe, I don't know whether 7-zip does, but I'm going to launch it. And again, this has to be performed on a system that's either running just an audit policy or one that is not running any sort of device guard enforcement at all. Okay, so I'm confident now that the system has all the binaries that make up 7-zip. I'm going to stop. Uh-oh. I have a typo, unfortunately. Well, fortunately, I think... that's a great question. I don't know, but I might have to do this one again. It's fine. So I'll let Scott entertain you while I undo what I've just done.
Yeah, so one of the tricks, and that's what Jeffrey is getting hit by right now, is that because we're scanning every file that gets laid down, if you've already installed something, I mean, you would pick that up normally as, say, part of your full system scan. But if you want to use Package Inspector to capture that, you really need a clean system because you want to make sure that you're reinstalling all the DLLs, everything that that particular application might use. I mean, just a small thing we ran into last night was we already had 7-zip on the disk, and then we ran it to install it and created the catalog. But then when we took it to the other machine, it didn't run right away, and we're like, oh, because we already had 7-zip on the disk, we didn't scan the actual executable that starts the installation. We had to go back and make sure that the first thing we did is copy it to the disk so that gets captured, then run the installer so that everything that gets installed by it gets captured. And like Jeffrey said, I don't think 7-zip does, but there is definitely applications out there that when you run them, they go to the internet, maybe try to update themselves or grab some other files. So you want to run through it at least once and make sure you've captured everything when you're doing the capture.
So is there a central repository for all this?
The question is there a central repository? There's not a central repository today. We are thinking of ideas around how we can enable the ecosystem. Although, like Jeffrey mentioned, we're going to have, over the next while, Win32 apps in the store. So it's likely you'll be able to get 7-zip, say, from the store. And in that case, you'll already have a known signature on it. And then for LOB apps, really most companies are going to have distinct LOB apps. So it's hard to have the central repository. But there is some thinking about some way to make maybe a community-led effort to make it easier to share policies that work across systems.
All right.
Oh, so
Go ahead and answer.
In terms of the scanning, obviously this is a one-time operation, but then you end up with the catalog, and the catalog does need to be distributed to every machine, but that can be done through your sort of normal system management tools.
Okay, so I've undone that, so 7-zip is uninstalled. I'm going to go ahead and start the scan one more time. Oh, okay. Okay, so start the scan. Again, copy the installer, run it. Okay, 7-zip is installed. And I'm not going to be fancy this time. I'm not going to do any of the optional command line options. And so I should see now, if I come over to the C drive, there's the output from the scan, produced actually 2 files. One of them is inspected package. It's a CDF file. And this is essentially the manifest that tells you every write operation that was detected. So you can open that up and actually inspect that the result is what you expected to see from that. And then the other one, we actually generate the catalog. If you do need to make modifications, so for example, if it picked up additional write operations that you didn't anticipate, and you want to remove those, you actually have the ability to modify the CDF file and then recreate the catalog file afterwards. And so let's just show you what the... So this is the CDF file, and this is just, again, the enumeration of the file write operations that were detected that were binary files during that time that the scan ran. And then it was compiled into the catalog. All right. And now I'm actually going to copy the catalog over to the desktop so I don't have to change my scripts completely. All right. All right, so what I'm now going to do is, last but not least, I'm actually now going to sign that catalog that was generated. So I'm going to sign it with a certificate that I created for my organization. We called it Device Guard, but you can call it anything you want. So this is my own signing certificate. Again, later when we've stood up that signing portal, you could submit the catalog to the portal, and we would return it to you signed as a separate option. And if I got everything right, it signed the file. And let me just... All right. Show now that I have indeed my signature on this catalog. So now I can take this catalog and distribute it along with the application to any system that's locked down with Device Guard, and it'll actually be trusted to run. Or, knock on wood, it should. Let's see if my demos work. Okay, so I'm going to copy the signed catalog to my USB drive. And we're going to go over to our other system. And this one now is actually running in enforcement mode. So I have the 7-zip installer, and it should be blocked on this system, and indeed it is. And so I'm going to just... So the catalogs just need to be written to a well-known location within Windows, and automatically the code integrity policy will pick it up.
Is there a recommended naming convention that you guys are proposing for security catalogs?
So the question is there a proposed naming convention? There's not one that we're proposing, but I think it's a best practice that you follow some sort of standard naming convention within your organization. But the catalogs can be named anything. There's no enforcement around that.
So by well-known, you mean that particular name?
Yes, exactly. That specific path, and it'll be the same path on every system that you encounter that's running Windows.
And it's documented at this time?
It should be documented.
I believe it's already documented. If not,
If not, we'll
will be.
document it. All right, so let's just... All right, let's see if I didn't screw this up. And now we got past the warning, and I can successfully install 7-zip, and I should now be able to also launch it, if I can find it. Voila. So, most of what we've shown here, while we don't have tight integration yet with management products like Config Manager or Windows Intune, can be accomplished certainly with Configuration Manager. All of the PowerShell commandlets, of course, can be executed as just existing packages and programs within Configuration Manager. They could be integrated into OS deployment, as additional steps that get performed by your OS deployment distributions. You can copy the files, obviously, through Configuration Manager, distribute them through Configuration Manager. One other thing, of course, if you have a lot of applications that you want to sign, rather than creating multiple catalogs, you could fire up the package inspector tool that I just showed and do all of the installations of every application that you need to sign that is not today signed, and create one big catalog that's just my line of business apps and deploy that. So you have a lot of flexibility in terms of how you actually conform your existing line of business apps to run on a device card system. Yes, sir?
Can you differentiate whitelisting the hash of the executables from creating the catalog file? From your standpoint, is one better than the other?
Yeah, I mean, the catalog is preferable for a couple of reasons. A big one is what Jeffrey just showed you, that you can install that catalog file and it takes effect immediately. Whereas if you're creating hash rules, applying a new policy requires a reboot. So ideally, the policy is something more static, right, that says, here's the signers I trust, or the particular files or programs I trust. And in the catalog, you can update as you're updating your software.
Okay. So just a few kind of closing points on this, and then we'll start talking about the virtualization-based security to kind of wrap up the session. So in the past, as Scott kind of gave you the history of code integrity, one of the other things that's been kind of undercutting our ability to provide a really, really secure environment is simply the fact that obtaining a signing certificate that allows an organization to sign something and make it able to run on any Windows system in kernel was almost laughably easy. The bar was not terribly high. There were some restrictions, but it was not difficult to obtain a valid signing certificate. With Windows 10, we're changing the rules for how a software vendor can actually get kernel mode drivers signed and running on any Windows 10 system. So we're raising the bar for how they establish their identity and prove the authenticity of the organization, and then we'll enforce that. And the drivers all have to now be submitted through Microsoft and signed with an actual Microsoft certificate before it'll actually run on a Windows 10 system. We do have logic in Windows 10 to grandfather in existing kernel mode drivers that had been signed previously that are still valid. And one of the options within your device guard policy is to actually require the stronger level of enforcement that comes with Windows 10 drivers. So you can turn off essentially the grandfathering logic that allows legacy drivers to run. Scott already talked a little bit about the last bullet here, taking your device guard policy. You can actually sign that policy, and that actually provides even stronger protection of your code integrity policy on your device guard managed systems. The only way to then update that policy subsequently would be to provide a newer version of the policy, again, signed with either the same signer or a signer that you specify in the policy itself as trusted to update the policy. So what that prevents is that just an ordinary administrator user cannot circumvent your code integrity policy. And then when the policy is signed, we actually measure that into the TPM. And it becomes part of this new feature in Windows 10 that's called Provable PC Health or Device Health Attestation. And this another feature integrated with mobile device management solutions allows you to actually provide control over access to resources based on the proven device health of the client. So AppLocker and code integrity. We actually think of AppLocker as part of our overall code integrity story. It's kind of an extension of it. Conceptually, we kind of think of the two as complementary, where the code integrity is more like the bouncer at the door of a bar or a nightclub, right? They're going to check your ID and before allowing you in, and they're kind of the strong guys who'll kick you out if something is really bad. But once you get inside, you still have to present your ID a second time if you're going to order a drink at the bar, right? And so the bartender then is what we're calling app locker. So the reason for having this separation is simply that because the code integrity policy is enforced at such a deep level of the operating system, and getting it wrong can be tragic, app locker allows you to provide finer level control over what can run and not on a system. That's, again, complementary to the code integrity policy that's being enforced. Both app locker and code integrity have been written so that they're manageable now through MDM as well as solutions like a configuration manager. So we've actually exposed app locker policy control through mobile device management. Yes? Are they also managed by GPO as well? Yes. So both policies are deployable through and manageable through group policy. The key difference is, as Scott and I had mentioned earlier, we didn't provide an authoring experience for your code integrity policy. Again, somewhat by design, with the intention that the management products step up and kind of build that experience integrated with their app catalog so that we have a much better end-to-end story.
So you can send out the updated policy, et cetera, but there's no authoring for your CI policy
Right.
within the GPO editor.
GPO, you simply point to the XML file, and that's that?
You point to the compiled binary. Yep.
Got it.
And then a couple of additional things just to kind of round it out for app locker. So app locker, of course, historically had only been able to manage user interactive processes, so applications that are being launched by the user. With Windows 10, you can now actually manage services or non-interactive binaries as well. And as we just said, management of that has been exposed through MDM and WMI.
Okay, so virtualization-based security, I talked about it just very briefly before. Basically, what we're doing is using hypervisor technology to create a secure environment where even a compromised kernel, even if Windows is completely compromised, this secure environment is still safe. There's three things we plan to do with this environment in Windows 10. The first is LSA credential isolation. There's been some other talks about that. Really, it's all the pass the hash stuff, all the credential theft stuff. We're going to store those credentials away in this secured environment, and even if somebody gets into kernel, it's hard for them to grab your credentials directly, or impossible. The second is a virtual TPM. This is a server-only feature. It was also talked about in another session around server health. But basically, what it allows you to do is have a TPM exposed to your virtual machines. So those virtual machines can then be encrypted. They can be BitLockered. So it enables a scenario where all of your VMs are encrypted, and when they come down to the server, they can get decrypted securely on that server without having to expose those keys to non-secured environments. And the third thing is what we call kernel mode code integrity. So we've talked a lot about code integrity. Specifically, the kernel mode component of this will now be able to protect with virtualization-based security. So in Windows 8, kernel mode code integrity ran within the kernel itself. So kernel mode code integrity said, anytime something else wants to run in the kernel, you load in through kernel mode code integrity, we check the signature, we say, yes, it's good to run, go ahead. But if malware gets in there somehow, it's howdy, peer. I can do whatever kernel mode code integrity can do, or even turn off kernel mode code integrity. And that applies not just to malware that we've somehow loaded properly, but any sort of buffer overflows. So if you can if you can overwrite memory, if you can, get your code injected into kernel, you can get that code to execute today. What we've done in Windows 10 with virtualization-based security is you have the hypervisor layer in there, and you see these two red boundaries. The box around the thing we're calling the secure world is in red, so that's hardened. So anything in the normal side, so the normal world being your normal operating system, Windows including user mode and kernel, can't get over into that secure side. And we've also strengthened the boundary between the host OS and the hypervisor. So traditionally, a hypervisor has protected a boundary between guests, so between the virtual machines that are running on a platform and the host, and between guests and other guests. And that has proven to be extremely solid technology. I mean, that's the basis for Azure or any cloud offering, right? The reason you don't need to have individual servers in the cloud anymore is because you're using virtualized machines. So that hypervisor protection, which is rooted in the actual hardware, hardware extensions in the chip, has proven to be extremely secure. Same technology we use within the Xbox, for example. So getting in there, I think, that's a boundary we can really defend. So now you have kernel mode code integrity running in that secure world. And if somehow in your normal world you are able to, inject, have some kind of buffer overflow, get your code injected into the kernel, you're still not going to be able to execute that code. All the pages have to be marked either writable but not executable, or executable but not writable. And the only way to change that is to come through the secure world and the hypervisor. And in the future, there'll even be hardware extensions which are helping us to support that separation. Yes?
What is the size footprint of VSM in terms of like RAM, disk, whatever? And are there plans on extending it beyond client Hyper-V to Hyper-V or Azure for server workloads?
Right. So there's two questions. One is, what's the footprint? We're still doing all the perf analysis in terms of what the perf impact is. So there is some perf impact. And there is also some footprint impact. I mean, the footprint impact is essentially the same as turning on Hyper-V today. So if you enable Hyper-V, that's what we need to do to enable this feature. The second question was, is this beyond client? Is this also for server? So actually, it is definitely also for server. Azure is doing a slightly different variation on this. But in terms of your own servers or other hosters, they will definitely have this same capability. And it actually applies both to the host OS and to guest VMs. So as we ship Windows 10 in client, it won't apply to guest VMs. But when we ship Windows 10 server, it will apply also to the guest VMs. So the guest VMs can also have this secure world for each guest that's protecting the rest of their image. So this device guard is an enterprise and server feature in terms of like SKU differentiation. I think we're doing, I'd say overall, lots of stuff in the consumer space. And as was mentioned by Jeffrey, more and more stuff's coming through the store, so you are seeing more signed code coming down. So I think there's definitely opportunities there. But in terms of device guard, as it is, this is an enterprise play. OK, so I already discussed this, I think, in the last slide. But basically, when you have kernel mode code integrity protected by virtualization-based security, the CI rules are still enforced, even if a vulnerability allows unauthorized kernel mode memory access. Even if somebody can change your kernel memory directly, they're not going to be able to overwrite your executable sections, and they're not going to be able to create anything that they've overwritten as an executable section. There is one big caveat here, and that's that not all the drivers will be compatible initially. So a lot of drivers have assumed that they could create their own memory and mark it executable, and that's not going to work when you've turned on virtualization-based protection of your kernel mode memory, because that doesn't look different to us from malware overwriting memory. So we are working with the partners to ensure that they create drivers, but it means at minimum driver updates, and also, as Jeffrey will speak to, there's new devices that will come with support.
Yeah, so what we've talked about thus far is all of the effort you would go through to try to generate policies and manage your existing devices that are capable of running any of these features. We are also working with many of our OEM partners and engaged with more than just are shown on this list to try to ensure that there are devices that are available to enterprises to purchase that come as DeviceGuard ready with all of the necessary features turned on, all of the drivers compatible with kernel mode code integrity enforced by the hypervisor, so that you can take those devices and actually deploy them with the full stack of DeviceGuard enabled. And the additional benefit being that the OEMs know already what is present on those systems, and so they can potentially offer services that allow you to that share the the starter policy essentially that allows just the things that are installed on those devices and just the hardware configuration for those devices to actually run. And then you would augment it with your own enterprise-specific application management policies. So that's DeviceGuard in Windows 10. Thank you all. Please do take time to evaluate the session. That helps to give us some feedback. And thank you, and enjoy the rest of today.
Thanks.